to introduce Dr. Indrani Bhowmick, who is going to be presenting today on materials analysis techniques. And with that, I will turn it over. Thank you, Indrani.
Thank you very much. So just a quick note, I cannot see anybody when I'm in the presenter mode. So I'll just kind of give the talk and then maybe wait for the questions at the end, if that's okay with everybody. So today's talk, I will be like more outlined in a way. I'll identify what you kind of define as a materials when it comes to in our lab, and then what you mean by the analysis we do, kind of break it down a little bit, and what are the ARC resources we have, and then at the end, there will be some time for questions and go back and forth on that. So for materials, the whole idea is like you are making things which could be material of different textures, different forms. Some are like liquids, right? So you have pure liquid, mixture, some dissolved liquid, or you have some solids, which could be a powder, a block of alloy. It could be a crystal or thin films, layered thin films, hybrid. Like layered thin film is one of the examples of hybrid material, where you have a substrate and you put different layers for your desired properties, and then you use that as a device designing concept, so actuators, and it could be different forms like gel cell or multiphase. So at the end, you come to analyze to do the analysis of your materials, right? So the way I see it is like you have this material, then you want to interact with some energy. Do I have the pointer here? I guess so. So you interact with some energy, and then you have an output or change, and that which you get as your data, and you do the analysis on that, right? So all materials have the molecular and atomic forms at the end of the day, and then you record the change after interacting with energy, and then you analyze it, and then you do something change about the material, and you do this cycle until you are satisfied. Then you either publish or present, or go further for making some devices. So in our lab, what we provide is that energy, right? Through a bunch of instrumentations we have. So I'll just kind of break it through into very simple thermal energy first, which we have two instruments, TGA and DSC. And then we add some magnetic or electrical energy source, which we have in PMS, magnetic property measurement system, and PPMS, physical property measurement systems. And then we also have this electromagnetic wave at the end, that's also energy. And in addition to thermal energy, we use the EPR. So I will go over those instrumentation, how they function a little bit, and also give lots of applications that can use these instruments. Okay, so with the simple one is this TGA, which is thermogravimetric analysis. We have these little pans. That little pans can hold, could be platinum, aluminum, or ceramic based on the material. If it's corrosive, you use the ceramic pan. And this little auto sampler we have can hold like 16 pans. And this is a little furnace. The sample goes in. And the way it works is we have a very balanced system. And this is your little sample here. And this is the furnace. When this balance is, and it has the infrared light, it's like a photodiode system to know the change of mass. And it records that change of mass and gives you as an output. So over time, this is your output data will look like. You will have a change of temperature because your furnace is warm heating, and there is a little thermocouple to warm up, and also to know that to record the temperature change of the sample and also the furnace. And then you see the mass change over time. So these techniques are used for a lot of fields. Like you want to know what is your content of material, when it's volatile or not, does it has absorbed water, moisture, or what temperature you should dry. The thermal stability, like you are making a polymer or a part of a car screen or something, or you want to see what is the thermal stability of that polymers or what material you are making. And then composition, multi-component system. This is like you can see the decrease of mass. You can put it back to the mass or the composition of the system we have. Other than that, batch-to-batch comparison is very important because in that you can actually see that if you're making a product that will be in market, if you're making every batch consistent or not, and many other usage. I'm not going to read it, but yeah. So you can see if it's oxidizing at some temperature or not, is it corrosive or not, this type of things. So this is a very simple example of, this is actually very standard example. It's like this calcium oxalate. When you decompose it, you see around 100 K, you have the water coming off as a gas, as a steam. And then you have the carbon monoxide gas comes off around this temperature near 400. And then at the end, you see the much higher decomposition when the calcium oxide and carbon dioxide gas comes off. We use this one also to standardize our, calibrate our system sometimes. So this is, just remember, this is a destructive system. You cannot really take your sample back and analyze this more. You just do a thermal decomposition over time. So here is a simple example of different polymers where you see that different temperature. So it's like if you want to use the polymer for some heat, somewhere it will use high temperature, you can choose the right polymer for that. And there is another cool method that in TGA, actually, we have a nitrogen source or a air, like you can decompose it, like do the thermal analysis under nitrogen or in atmosphere. Here they're showing that because this compound has a lot of carbon-based material, it could not decompose under the nitrogen environment in this picture B, where in the A, it can decompose much different. The picture, the decomposition portfolio looks much different in air. And that could be important sometimes for application purpose. The other instrument we have is a DSC, which is differential scanning calorimetry. So with the word differential, hopefully it tells that you are going to send some temperature to your sample with a reference there. So where you will warm it up or cool it down in this temperature range, -90 to 350 degrees Celsius. And then your output at the end is a heat flow. What's the energy, how much heat is being flown to your sample versus your reference? So here, this is how it works. This little place has a little cell and it's a furnace. There are two spots. One is the reference and other one is for your sample. So you kind of seal your sample in a little capsule here and then put in those little spots. And then, so we actually has an auto sampler which can move and get here. We have the plate for 50 sample holder, which can grab your sample. So you can have a series of experiments going at the same time. Not at the same time, like one after another. So anyway, in the reference you have in this little cell, you have one reference and you have one sample platform where actually you hit the both reference and the sample at the same rate. But what you record with your temperature, here this T0 thermocouple, that what is the difference between the reference part and your sample platform. And then this temperature difference you use, because your heat flow is always the same, it's flowing the same heat, and then you use with all those equations at the end to give you the total heat flow of that of your sample here. So what you analyze is like kind of glass transition, and then if you have a crystallization in your sample, you'll see a spike in your heat flow, and then if you have a melting, you'll see a dip because heating takes more latent heat. So you will see that, and then you will go up, and if you have like some kind of other phenomena change like cross-linking or polymerizations happening, you will see some change. And then if you have oxidation, you can see a big change there. So the usage for this is like just seeing reproducibility of your sample, thermal stability. Like, if you have a polymer or a microwave bag, for example, and you tell like, well, discard after 5 use, or use this one, discard after that many use, or something. So this could be coming from this behavior, that how many reproduced behavior you're seeing, and after that you think your material is not good enough for thermal stability maybe. And then you have this decomposition kinetics of materials. So I will kind of give you some quick example. So this is a example from a pharmaceutical journal where they are actually aging it for 32 hours, which means that they're keeping the sample at 65, 75, 85 degrees Celsius for 32 hours. And that's where they're seeing that the sample, when it's coming back, they have a little crystallization probably. So it's not anymore amorphous in this case. So if you want the sample to be amorphous and you want to see what is the temperature range, you should keep it like, more amorphous, then that should be the range, probably below 65 or something like that. So you can determine those temperature sensitivity of your sample using the DSC. There is another example of pH dependence here. So they're seeing that based on the pH of the solution, they are folding and unfolding more proteins, and they can detect it in the DSC measurement as well. So I'm going to the next, like kind of putting another layer of energy on that, from thermal to the magnetic field energy here, which we use the MPMS, which is called magnetic property measuring system. Again, our energy source here is temperature, where if we use oven option, we can go up to 1000 degree Kelvin. 1000 Kelvin. And then if we sweep the DC magnetic field, it can go plus minus 7 Tesla, our AC magnetic field. So DC magnetic field means like you have a constant field going on and you are seeing your sample in that magnetic field, which you can choose any little to any high field in it. It's very sensitive. And where AC magnetic fields, you are oscillating, so you're magnetizing, demagnetizing at the same time. So you're oscillating a magnetic field and seeing the property of your sample or material here. Output after sweeping temperature field is actually only one input you are getting is magnetic moment. And mostly it used for thermomagnetic properties of a lot of type of samples. So I'll go show you how the system works a little bit inside, very simple way. So this is the little VSM head, which is called vibrating sample measurement. But this little head, there is a little window where you can see your sample where it's located through the rod passing through this whole chamber here. And there is a liquid nitrogen bath here where your magnet sits at very low temperature. It's 4 Kelvin. At liquid helium temperature there. And there you have this magnetic coil, and you see that blue line here is your sample rod, and your sample will sit just here. A 5 millimeter by 5 millimeter sample will sit there, or 5 millimeter cube, if you can think like that, will sit here for your sample measurement. And the helium flow and all of the like lots of heaters, lots of little impedanceator in the flow exchange, and these will control the temperature and the magnetic field of the whole system. So now here are a couple of modes you can do the measurement. So the way it works, like in this picture, the previous one, you saw that the sample is sitting here and you have this coil, which is the magnet around it. So in the end, you have these magnetic coils there, right? And when you have the sample, this is the top window, you can move the sample in 2 ways. One is called DC way, where you move the sample all the way through the magnet up and down. So the word squid is like interference, superconductive. You interfere this magnet here. It is a very uniform magnetic field, and by moving the sample through that, we just interfere the field, and that gives us the response. Okay, so the two ways we move is one DC, where the sample goes up and down, and other one is the squid VSM, where the sample just vibrates in this very uniform coil field here. And then you get this response as soon as the sample passes this uniform area, you get this big response of the voltage change. And then you feed that data, which gives you the magnetic moment. So this is just the response with no sample in that, which is telling that the sensitivity of these both modes are kind of comparable. And at the end, the sensitivities, they are saying that 10⁻⁸ mu, and that can go up to 100 mu, which is pretty strong signal. So there are some about the sample preparation. So you saw here this where the sample will go up and down. The long thing takes, this is our sample rod, which is will just hold the sample. This is a very standard brass rod. Other than that, we have some quartz rods then where you can put like, solid samples, which is not powder. And if it's powder, we can put into this little holder and snap in those brass rod. If it's liquid, we have some liquid holders, but the best method is sealing it in quartz rod, like quartz tube like that under vacuum, because when the sample will go in and it's very cold because it's a temperature dependent measurement and you have oxygen in those quartz tube, which can liquefy and cause a lot of problem. So you don't want to seal them under vacuum or in a very inert environment. And then you put a sleeve of just drinking straw, which has very little magnetic response, to be honest. Like it's like not enough diamagnet, not enough paramagnet to interfere your data. It's pretty clean. And you put that sleeve and we can just mimic this whole rod and put it inside. And there are other method can be adapted to based on how the sample looks and what it is. But at the end, it's that a very little sample size. It have to sit into this window. And then we can put it in the MPMS. So the other system we have very comparable for the magnetic part, but it also has a lot of electrical energy. Not a lot of energy. It has electrical energy input-output method on top of the magnetic one. So which called physical property measurement system, okay? So here again, the energy sources is like temperature, very similar to the MPMS I showed. And then we have these sweep the DC magnetic field, you can sweep to 9 Tesla, which is higher. And then we have electric current and voltage input as well. And the output will be magnetic moment, but then you have electric resistivity, you can see thermal conductivity, you can see the heat energy, like the heat flow at the same way, but much, much more sensitive. And these all properties can be used for thermomagnetic property, thermoelectric or magnetoelectric properties of samples. So this system are used generally in temperature, like the temperature magnetic measurements and electrical transport. It has some option where you can use the magnetoresistivity, Hall effect, IV curve, lot of engineering and physics people are interested in this kind of measurements. As usually, heat capacity measurement helps for phase identification and phase transitions. And then other than that, we have thermal transport and simple magnetometry, which also we have in PMS, just more sensitive in MPMS compared to PPMS. So this is how the whole system looks inside, like a diagram, schematic diagram. Let's not look into that. Our interest should be just this little isothermal region, because we want to have an isothermal region when we will put our sample. We should not. So we need to know the exact temperature, because temperature is the basic energy we are putting here. So we want to know that. So we want to, this is where our focus is. This is 2 magnets and our sample sits in this isothermal region, and there is a lot of helium flow and bath to control the temperature. and other controls there. So in that little place, we have something called puck that goes in the PPMS. So this is like different pucks for different measurement. This is resistivity puck for electrical measurement. Universal puck is just to design your own experiment, what you want to measure. This is a temperature transport puck, TTO. It's a little sample, and you have like you're seeing how much temperature is being transported. For example, you're having samples and you want the insulator, you want a good insulator, then you want to see very less response in temperature transport, something like that. This is a heat capacity puck. This is a rotator. In this rotator puck, what happens very similar to resistivity, but then we have all those gears that can rotate the sample along the magnetic field. I'll show later how it's why it's important and kind of interesting. And there is a VSM puck, which is very similar to a squid coil you saw in the MPMS, and sample sits between here. So at the end, all those pucks has this bottom looks the same, right? And it has all those 9 pins, and those pins goes here. And that's how it communicates with the software and your input information and gives it the output data at the end. So the interesting part of PPMS is it just all those platform gives you option to put any sample. So as long as you can mount the sample on those pucks and you know what you are measuring, a lot of properties could be measured, and it's kind of that's why it calls physical property measurement system. It's like very general name for an instrument. Okay, so let's go into some applications a little bit. So we talked that we have lots of magnets in PPMS and in PMS and the control over it. So where we do use the magnets, it's like we do have magnets even consciously, unconsciously everywhere in our life. We have it for navigation, to magnet electronic devices, all type of permanent magnet, electronic motors, or the electromagnets, or different sensors, or your credit card or sensor card to get into our building and everything. And lots of kid toys and jewelries and everything are being just magnetic. So we are seeing them everywhere, and those are materials, and they're being made in many ways. Sometimes they're very little magnet, like nanomagnets. Sometimes they're just in a solution or molecular form, or in a very hybrid form where they're being used. So here I just noted few of the applications of little magnets, nanomagnets, or molecular coordination chemistry has some magnet. They use PPMS and MPMS. One of the biological application will be MRI contrast agent to study their very initial properties, and not only initial, like a lot of advanced properties also could be studied in APMS. Environmental biology and geology has importance of magnetic measurements, and photomagnetism is very interesting because photodiodes and sensors also in magnetic field combine those measurements, and we can do that here using the APMS and PPMS as well. So very basic. Who doesn't have we may have magnetism background, like what paramagnet diamagnets are a long time ago, but I will just go briefly over a little bit. The basic classification of magnetism. So at the end, we are getting magnetic moment, right, as an output of the data for MPMS or PPMS. In that case, what we want to see is how the response should look like. So the basic classification of magnets are paramagnets, diamagnet, ferro, antiferro, ferro-ferri, and antiferromagnet. So what is paramagnet means? When there is no magnetic field, all those little spins are, think about little bar magnets, and they are just random. So you don't have any magnet because they're canceling each other all the time. You don't feel it's a magnet. But as soon as you have a field, they all align up and you get a magnetic moment. You get a response. For ferromagnets, they all get aligned and they wait. Even though you take the magnetic field off, you have some remnant magnetization, because like a piece of iron, just simple, just magnets, you have neodymium magnet, for example, or the fridge magnet you are putting. So they are all aligned, and they had a time before they will come back to this randomized space, or sometimes heat can do that. So you don't want to put your magnet in the heat and they will lose their magnetic properties, right? So that can be studied in MPMS, BPMS, that what that temperature is or how long it will be a ferromagnet. Antiferromagnets has a lot of applications as well. It's a little more complicated than ferromagnet, because at the end, it's like here also you are seeing all the spin aligned, but opposite to each other. So you're looking for something to be zero. But that has its applications as well. And then ferromagnetism is most interesting in a way, because here you have parallel and anti-parallel spin in your material. So now you have a control that how much you want to make the parallel and anti-parallel interaction to tune what moment, what temperature you want, what magnetic field you want, or how you want to design your device. And that's where like a lot of science actually relies on the ferromagnetism. So what happens with the temperature here, that we see that at a temperature, your if all the spin will get random at the end anyway, and that's different name for that, has like critical temperature at this end, I can say. For this is example for a ferromagnet, and this is example for a antiferromagnet in this case. So here are again some very basic response how we will get. So for example, if you have a diamagnet, you increase your field, your magnetic moment will decrease. If you have a paramagnet, it will be just opposite to that. It will increase, because now they're going to being parallel to each other, so your moment is increasing. For your ferromagnet, it will increase first, and then when they're all like lined up, there is no way to line up more, so you will see kind of a saturation. For your antiferromagnet, you will see a decrease very similar to here, but only the difference is here is, even though there is a field, in this case, you will have a positive intercept. In a way, even though you have a field, you have a zero moment. So you need a little bit higher field to make them paramagnet. So at one point, they will be like paramagnet. And then ferromagnetism is again very similar to the ferromagnetism. At the end, you will saturate. But by changing, the control comes here by changing these moments, or by control synthesis, or whatever the method you make it, you can change the slope and this temperature. It's not like a permanent magnet in that case. You can design it more on that. So here is a little equation how it works. I'll just kind of go over the next example rather than that. So here I have this example of a bilayer thin film, where you can see there is a substrate and there is a nickel iron and nickel chromium layer on top of the substrate. And if you change the angle of that film, you have different magnetic response. You can see that the corrosive field, like the field where you have the zero magnetic moment, is higher when it is 90 degree, and also your saturations are different based on the angle. Now this can have an application where you want to put this film as a sensor somewhere. What angle will be better? Or how much coverage you are having. This type of information can be obtained by this angular movement of this substrate here. Oh, not substrate, sorry, the sample here. This is a very classical example of a molecular magnet. Here you see this hysteresis loop. This molecular magnet also showed hysteresis loop long time ago, and it had at that time, quite a bit promises. It had other complication to make it applied actually in devices, but promises that we can make the magnets even more smaller and make smaller devices or smaller memory chip or something like that using molecules instead of materials or some solid state 3D material. Here is a example, this one called spin crossover system, where you can see at some temperature, this sample has no magnetic moment, almost or very little, and then it jumped up around the temperature too. So what happens that inside that molecule, it goes a change from low spin to high spin. I'll not explain that, but using this thermal hysteresis, so it's like similar, but when you cool versus heat, the cycle is different. But using this method, they made these little flower petals, like when you are in low spin at a particular temperature, you see the petal kind of closes and then it can be open. And sometimes if you have a sensor that, you touch those petals or whatever material you're making will trigger a response, then you can use these materials actually to do some kind of sensor design. So we are very always want to know what the biological applications or where these are important, because we are human being and we like to know where it applies in our real life. So there are some examples where the instrumentation can be used for identifying different type of magnetic nanoparticle or magnetic molecular level particles. So some are applications. This is a very nice book, actually has a lot of nice examples of magnetic measurement techniques and its applications. So here you can see we can do labeling. We use a MRI or MPI. MPI is magnetic particle imaging. We use the magnetic field and this oscillating field in biosensing. We can use that for hypothermia, so we can send molecules that can have that behaves differently with different temperature, magnetic nanoparticles, and we also can do the bioengineering as well to orient something in a particular direction we want by using magnetic field, and we can study what orientation, what field, and what's their sensitivity and or temperature sensitivity and magnetic field range. They are functional actually. And then drug transport and delivery also, we looked into magnetic nanoparticle as well. And here is a very funny, cool, I don't want to say funny, it's cool example, I will say. So we know in the social insects like honeybees or ants, they have a directionality sense, and that is somehow related to Earth magnetic field. And so there is this cool study here where they actually took the head, the thorax, and the abdomen part of a honeybee, and they found that the magnetic particles are more concentrated in the abdomen part, not in their head or thorax part. And there are studies about that, how if they are in an altered field, will their social behavior will change, and how many generations is it going to be retained or not. These type of studies are being done on that. And this whole measurement was done in MPMS actually. You made sections of head, thorax, and abdomen, you put it in MPMS on the sample holder, and we got this hysteresis for the abdomen, but not so much for the other one. And we found that they actually showed that these are single domain magnetic particles. So if you remember, I had the picture of domains in the general second slide. So in those cases, they determine that those are single domains. So they're very much like you have a field, they will align. You don't have a field, they will align in different direction, or they will not align, something like that. And because a single domain, it can range, it can retain more memory in a way. I'll get to that later, maybe if we have time. Another example in the art science, so geomagnetism, paleomagnetism, rock magnetism, a lot of places has the uses of MPMS and PPMS. So this is a very well-known but unique measurement they do is first order reversal curve fork measurement. So what is it is like we saw the hysteresis. And then in hysteresis, what happens that sometimes we have this anhysteric remnant magnetization. The reason is the rock sample is not a single domain. It has a lot of impurities. It has little defects and a lot of like the simple geometries, geological samples are not as uniform. So in that case, we want to see the field, magnetic fields to reverse that magnetic moment are not always the same. So by changing little field, we create this big curve of hysteresis, but at the end, taking the first order reversal of that or the kind of derivative of that, we can create this fingerprint for some sample. So here is an example here. So this is a multi-domain magnetite sample, and this is a like I'd say single domain, but powder like polydisperse. Like it's not like it is single domain, but that doesn't mean the sample is exactly same size. The mean size is that, and they have this sample, and then they create this diagram by using this series of hysteresis, and that uses as a fingerprint to see that in this mountain, in this Yucca mountain, they found in Nevada, they got the sample and found that it has this sinking domain magnetite particle in that. So this type of usage we have for geomagnetism, and also it uses like sometimes that what was the temperature when this rock was formed and dates back to the geological phenomena at that time happened in the earth billions years ago. And this kind of studies had usage for those PMS and PPMS instrumentations. So another thing I would like to highlight here is this magnetic refrigeration, which is a very, I will say, newer techniques that people are trying to develop for cooling, which works almost the same way like we have, or like the gas compression. So we compress, which heats the sample. So we have that. And then you retain some when you release it, and then it released that heat that had, and then you go through that. So you kind of use that compression method, release the heat, abstract that heat, compress more, this method to do the gas compression. It's same way this magnetic refrigeration is, you have some samples which undergoes in an isothermal magnetic entropy change. Means when you have that, it holds that energy in that as a heat energy, and then it can release when the magnetic field is not there. So we can, there is a cool example I found actually in this Nature Communication, which came out a couple of years ago. So their design is to liquefy hydrogen by using liquid nitrogen and a series of this type of compound, which can go this isothermal magnetic entropy changes actually in this case. So what they used is actually the PPMS, this heat capacity measurement, the little puck I showed, that's what they use here. So what they did, they made a series of this alloy with europium. So if you go here, they showed that it has this first order, but this one has the second order phase transition, SOPT, which they don't want, because the second order phase transition is kind of like opposite to what you're trying to do in a way. So we want to have only first order phase transition. So what they did here, again, you have this series of compounds they made by changing the cobalt and the iron ratio, and you can see that there are some first and second order. The black line has second order because if you take a derivative of this black line, there will be two peaks, you can think, or you can see this S shape, which they don't want. They want to have only first order of the phase transition, and they made this series of compounds, and they found, well, this ratio of cobalt 96 iron 04 is very good. or they did this ratio here. They found that this one has the second order, this one does not have the second order, and that's what they chose. After that, they, instead of doing this 0.5, they found that, well, the temperature, the response is much higher. So in a way, the heat capacity, specific heat, it will hold more heat. If we use a little different ratio, this is done also in PPMS using the heat capacity. And then using the similar heat capacity, you can see also the change of magnetic field. So PPMS has a magnetic field which can be swept while doing this measurement, and temperature can be swept, and the magnetic moment could be measured. And after doing all these, they created this series of alloy, or they found some of the information from literature as well, and they then designed this device at the end, which mimics this actuator model, that they, instead of taking this hafnium cobalt in europium cobalt, they will use some alloy to make this device. They can and reach that temperature. So, but this whole study was done in something that in the physical property measurement system. The other one Coleus I'll talk is, this is actually from here from the physics department done. So the resistive EasyPark and this horizontal rotator that been used. So at the end, what we have here, that this is the platform to put your sample, and you have those little pads, which are conductive pads, where you connect to measure your current and voltage. So you put your sample there and you connect them with wire in those pads, and then it can be here as well similarly. And then this whole thing goes, or the puck goes inside the PPMS, and then you measure your sample. So what they measured is a topological material. So what is topological material is you change the surface, you design the topology of a substrate the way you want, and that can have directionality of their magnetic moments and the electric, the way the current will flow and things. So it's very specific for like you designing a chip, which way you want to direct the information of the current. These are very important for those type of devices. So here, by using this rotator, what you can do, that you see a spring and all those things, you can rotate the sample sitting here against the magnetic field in the PPMS, which is very one direction. And that means in a way you are seeing the change of the field direction. So you don't rotate the field, you rotate the sample against a field that is in a particular direction. And you can see this I and V, and you can see this I and V if it's very tiny, but here, so the sample was like kind of connected like that. Let's think this is a schematic diagram. But then what they see that with the change of the angle of the field, when they're using this 9 Tesla field here, they are different based on which angle of the field they are. And if they're having the current, they can find out which at direction the current flow is highest, and that also increases, the change of resistivity increases. So this is, and then it has its usage based on what you, what this type of materials can be used, like sometimes like field sensing applications, storing informations, or very small device designing, kind of electrical sensors. So, okay, this is where my PPMS and MPMS ends. And the last one I would like to talk is a little bit about the electromagnetic and thermal energy source we have, which is electron paramagnetic resonance. But this is not a magnetometry. This is a spectroscopy, or this is not electric things. This is a spectroscopy method, because it's using the electromagnetic wave, but using a very, very low frequency, microfrequency, microwave range of that. The temperature control we have here is 4 to 300 Kelvin using liquid helium. And we can sweep the magnetic field here, but this is actually not, it's a sweeping field, it's not a constant field. Like it's not like NPMS or PPMS. And the output is your response to the atom which is interacting with the unpaired electron. So what you can measure here is free radicals, metal species, which are number of electrons. You can use it for excited states. And the way it works, the reason it is in my spectroscopy is like you have a source, which is sending you the microwave, and that goes without interacting with the sample to detector. And then a part goes through this circulator, goes inside. Here your sample sits here, and then you actually go, the response goes back and goes to detector. And that amplifies, and then you get the response. So what happens that at the end, you are seeing the difference between the microwave that is coming without interacting with sample and the one coming with interacting with the after interacting with your sample to the detector. And your sample sits in this magnetic cavity. These are electromagnet with lots of copper coil in that and very uniform field. And the way it works like called Zeeman effect. So Zeeman effect is like every electron, when you have like, you are not having magnets, or you have electrons all the way around, like we know, like paramagnets, but they're not always, they're random, and so they're canceling each other. So in a way, when you apply a magnetic field, the electron can have an up spin, can have a down spin. It can align with the magnet, or it can not align with the magnet based on the spin of the direction. So in the electromagnet, you have a direction, right? In the north and south pole. So you are creating that directionality in the magnetic field as well. And when you increase that field, some electron will align, some will not align. And then what happens that at one point, this microwave frequency will resonate with this energy at a particular field. You will see the absorption of energy, and the response will be the first derivative of that energy, and that is your EPR signal. So when you have one electron or one radical not so much interacted, very uniform environment, let's say, then you will see that one peak, and you know, yes, I have a radical. So, but more, to make it a little more refined, we can see also hyperfine and super hyperfine interaction here, where is a effect of a nuclear spin interacting with the electron spin. In this case, nitrogen has a hyperfine electron, and so you will see a little more splitting on those. First, this is the electron, and then you will see the hyperfine interactions, and you will see some more splitting of those. And you can see very precisely those peaks as well. Here is one example where they actually quantified two types of radical. One is this butyl radical and the isobutyl radical. And this is the sum, so quantitative analysis. And then there is a temperature option I like to told, but this is not as connected. It's a completely different device that goes into a helium jacket. Your sample kind of sits into that. So it just feeds helium into real-time helium, and it's not a sweeping temperature. You set a temperature you want to measure your sample. It's very different, a little different than the other two measurements we have. But that could be important sometimes, because here they saw that this hydrogenated zinc nanoparticle has much better response of those type conductivity or the defects they had, or hydrogenated part has more response at very low temperature, but almost not there at 80 Kelvin. So if you want that one to be applied or application wise, then maybe that's what, or vice versa. What's your goal of the material analysis is. Here is one last cool example from the Bruker website, actually. They used the same EPR we have for doing the uranium, starting some uranium series coupled to the UM series to actually determine the they actually used that one and compared with each other to like determine the time of the when it was actually happened, the life of the fossil. I can't talk. The age of those fossils teeth. Okay, one of our user in the radiological health science is using our EPR to create the radiation dosimetry system using this L-alanine. So it's just different radiation dose creates different amount of intensity of the alanine peak absorption you saw. And based on that, if you have a calibration curve, you can create some kind of device. So EPR has a lot of, this is just a general application like other system I showed. EPR has a lot of applications in chemistry to see the coordination chemistry in organometallics, the presence of radical or their interactions with the system and the environment and the solution, electrochemistry, redox and kinetic science kind of could be has a very good use of EPR. Other than that, you can see polymer degradation, contamination, or radical generation over time in semiconductors or many other type of materials. A similar way in the bioscience, they are kind of chemistry and biochemistry is kind of, has a lots of overlaps. So you can use the stability of RNA and DNA mechanism. You can do the spin labeling study using EPR, and oxidative and antioxidant study can be done EPR because that's what it looks for, like a your presence of radical or oxidative species. And with that, I will finish my talk today, and I hope I have some time to discuss.
Thank you, Indrani. We'll open it up for questions.
Sure.
I see a hand raised.
Sharing so that I can see people.
Ronnie, please. Yeah.
Wonderful. Indrani, lovely talk. Loved it. I have one question for you about the magnetic refrigeration stuff. Mm-hmm. So do you anticipate that technology sort of replacing vapor compression refrigeration at any point, or do you expect it to be used more for like exotic applications like hydrogen liquefaction and such?
I think there are some device designing happening because in last material conference I was in, I saw people are actually putting those samples on some, layers and thin films, and they are also doing MFM and like they're trying to make this alloy into devices actually, and doing the AFM and MFM study on them. So it's not the only application. This is just one.
Right.
Yeah.
Right. Thank you so much.
Other questions? Okay, and if you do have questions and aren't comfortable talking now.
I have one question.
Yes, chime in, please.
Nice talk, Dr. Indrani. Thank you so much. So I'm interested in EPR. So you said you can use it to measure the free radicals of the samples. So can you, if I have some polymer samples, polyethylene, for an example, so if I have them oxidized, so is there any way that I can quantify the free radicals in the samples?
Yep, you can. Yeah. For just to quantify, you have to have a known amount, and then you can create, like if you oxidize more. So if you know how much you oxidized, we can just create a calibration curve, and you can do that. Yes.
Initially, I have the reference sample, and then I have oxidized them for like 10 months. So you mean I can measure the degree of free radical formation by month? You mean?
Yep, you can do that. Sure.
Do I have to dissolve my sample?
No,
In
this is
paper?
not destructive method, so your sample will be fine. It just have to fit into a small tube. A 10 millimeter diameter tube works as well, but smaller is better. But yeah, I know you
Okay.
do DSC, so yes, that's
Yeah.
plenty of sample, and you don't have to destroy your sample.
Okay. Thanks so much. I'll contact you regarding that. Thank you so much.
Okay. Yeah, sure.
Okay, I think that we will stop here then. And if you do have any follow-up questions, feel free to reach out to Indrani. All of the contact information is on the ARC website. For those in attendance, please do join us next time for May 1st for Dr. Alyssa Winter-May's presentation on MultiTOF. And thank you all for coming. Thank you, Indrani.
Thank you, everybody.